The question says that a storage battery of car has an EMF of 12 volt. If the internal resistance of the battery is 0.4 ohm, what is the maximum current that can be drawn from the battery? So here the question is, there are two components. There are one component in this circuit, that is a battery of EMF 12 volt with the internal resistance of 0.4 ohm. Now we have to find out how much maximum current can be drawn from the battery. So the maximum current can be, in order to find out the maximum current that can be drawn from the battery, we need to get rid of all those extra components. So we have to close the circuit with just the battery with the internal resistance of 0.4 ohm. So after closing this circuit, we can give the expression for current as potential difference divided by resistance. Now here resistance is just the internal resistance of the battery, no other component. So V would be equal to 12 volt and the resistance would be equal to 0.4 ohm. Now using this formula, we get the value of maximum current as 30 ampere. That is, if there is no any other electrical component connected to the circuit, we can get a maximum current of 30 ampere with this 12 volt battery and internal resistance of 0.4 ohm. Thank you. The question says that a battery of EMF 10 volt and internal resistance of 3 ohm is connected to a resistor. If the current in the circuit is 0.5 ampere, what is the resistance of the resistor? What is the terminal voltage of the battery when the circuit is closed? Now given here the question is, this is the circuit where there is a 10 volt battery and the internal resistance of the battery is 3 ohm, and in series there is a resistor of unknown resistance connected. We have termed it as RO, and we have to find out what is the terminal voltage across the battery of the circuit. So we can apply Kirchhoff's loop rule over here, that says that potential difference across a closed loop is always equals to 0 in a closed circuit. Now we can start from the battery over here from this point. Now from this point moving leftwards towards the direction of current, we can see we have met here a negative of 10 volt, so we will write minus 10 volt. And since current flows from higher potential to lower potential, so this potential, the potential at left point is always going to be higher than the right point if it is going from left to right. So it would be written as potential difference across the resistor R can be written as R times I, that is this one. Similarly across this resistor also, moving here, we can write it as I times 3 ohm. Now we have been given that I is 0.5 ampere, so we can substitute the value of I in this equation. Now we will get the formula. Now we will get the value of R as 17 ohm. Now we have to calculate the voltage across this cell, that is this cell. Now potential difference across this cell is will be composed of the cell, that is 10 volt plus its internal resistance. So we can move from here, from the left point of the cell. Now it is 10 volt minus, since we are moving in the opposite direction of the current flowing, so we will get here the lower potential, so it would be equal to minus of 3 times the current, that is 0.5 ampere. So we will get a value of 8.5 volt across this battery. Thank you.
The question says that at room temperature, that is 27 degrees centigrade, the resistance of a heating element is 100 ohm. What is the temperature of the element if the resistance is found to be 117 ohm, given that the temperature coefficient of the material of the resistor is 1.7 × 10⁻⁻⁴ per degree centigrade? Now this question talks about the relationship between resistance and temperature, and which is given by resistance as temperature T with respect to the reference temperature T0 is equal to R0, that is the resistance at the reference temperature multiplied by 1 plus alpha. Alpha is the thermal coefficient of resistance and it is material specific, multiplied by final temperature minus initial temperature, or the delta T. So in this question we have to find out the value of final temperature given the final resistance, initial temperature, thermal coefficient of resistivity. So after substituting the values in this formula, we can easily calculate the value of T because this is the only unknown over here. Now substituting the values, we will get T equals to 1027 degrees centigrade. That is the final temperature at which the resistance was 117 ohm is 1027 degrees centigrade. Thank you. The question says that a negligibly small current is passing through a wire of length 15 meter and uniform cross section of 6 into 10 to the power minus 7 meters square, and its resistance is measured to be 5 ohm. What is the resistivity of the material at the temperature of the experiment? So we have to find out the resistivity in this question, and we know that resistivity is related to the resistance as R equals to R as the resistance is equals to resistivity rho multiplied by length of the conductor divided by area, cross-section area of the conductor. Now resistivity of a material is a material specific property that quantifies how strongly a given material opposes the flow of electric current. It is represented by rho, as we saw in this expression. Now in this question we have been given the length, that is 15 meter, cross-section area we have been given, and resistance is given 5 ohm. Unknown is the resistivity rho, so it can be easily found by rearranging this formula. So rearranging and substituting the values, we will get a value of resistivity as 2 into 10 to the power minus 7 ohm meter. Thank you. The question says that a silver wire of resistance 2.1 ohm at 27.5 degrees centigrade and a resistance of 2.7 ohm at 100 degrees centigrade. Determine the temperature coefficient of resistivity of the silver. So this question talks about the temperature dependence of resistance, that is given by the formula R at temperature T equals to initial temperature or the reference resistance at reference temperature R naught multiplied by 1 plus alpha, that is the temperature coefficient of resistivity, multiplied with delta T or the difference in the final temperature and the reference temperature. So in this question we have been given the initial temperature, initial resistance at that temperature, final temperature we have been given, and the final resistance at the final temperature has been given. Now in this formula we have been given all these 4 values, that is RT, R naught, T and T naught. We have to calculate alpha. So in this substituting all these values in this formula, we can easily calculate alpha. We will get a value of alpha as 0.00394 per degree centigrade. Thank you. The question is saying that a heating element using nichrome connected to a 230 volt supply draws an initial current of 3.2 ampere which settles after a few seconds to a steady value of 2.8 ampere. What is the steady temperature of the heating element if the room temperature is 27.0 degrees centigrade? The temperature coefficient of resistance of nichrome averaged over the temperature range involved is 1.7 into 10 to the power minus 4 per degree centigrade. Now this question is using temperature dependence of the resistor, which is given by the mathematical formula RT, resistance at temperature T, equals to R naught, that is the reference temperature resistance, multiplied by 1 plus alpha, that is temperature coefficient of resistance, multiplied with delta T or final temperature minus initial temperature or the reference temperature. Now in this question we have been given the potential difference, that is constant in this temperature range, I naught initial current through the resistor, IT, that is the final current through the resistor, initial temperature we have been given, and the temperature coefficient we have been given. So we have to find out what is the steady temperature, that is T final we have to find out. T initial is given and we have to find out T final. So calculating the initial resistance, we can use this formula V by I. Since potential difference is same, so V would be equal to 230 and initial current is 3.2 ampere. So we will get R naught or the initial resistance as 71.875 ohm. Now final resistance we can also calculate, which can be calculated using the same formula, just using the final current or the current at temperature T. We will get a value of 82.143 ohm. Now we know RT, that is the final resistance, R naught, we have been given alpha, we have been given T naught. We also need to find out T, so substituting the values we will calculate for T, that is the final temperature. Now T will be 867 degrees centigrade. Thank you.
The question says that determine the current in each branch of the network as shown in figure 3.20. So this figure shows a network of resistors and a cell, and we have to find out current in each and every branch. So let's proceed with the Kirchhoff's loop rule, which says that potential difference across a loop is 0, and we know that current flows from higher potential to lower potential. We have decided to go with 3 loops. The first loop is A, B and D. The second loop is B, C and D, and the third loop is A, B, C and E, that is this outer loop. So in the first loop, that is ABD, we see that we have assumed the current in this direction from A to B. So the potential difference is going to be positive from A to B because the current is flowing from A to B. So we can write it as 10 times 10, that is the resistance, times I2. Similarly, in the arm BD, we get 5 times I4. Now in arm AD, now the loop direction is opposite to that of the current, that is current is flowing from A to D, but our loop is from D to A. So we will write it as minus of I3. Now equating it to be equal to 0, we see that it is 2I2 plus I4 minus I3 equals 0. Now similarly in loop BCD, we see 5I2 minus I4 minus 10I3 plus I4 minus 5I4 equal to 0. This will give us I2 minus 4I4 minus 2I3 equals to 0. Now similarly in the loop ABCE, that is AB, C and E, we will see that 10 times I2 plus 5 times I2 minus I4 minus 10 plus 10 times I1 would be equal to 0. Now this will give us 5I2 minus I4 plus 2I3 equals to 2. Now rearranging these equations, we will see we have 3 unknowns, that is I2, I4 and I3, and we have 3 equations. So after solving this, we will get the value of I2, I3 and I4 as I2 equals to 4 by 17 and I4 equals to minus 2 by 17 and I3 equals to 6 by 17. Now we can find the current in each branch as it is in the form of either I2, I4 and I3, and we can write I1 as equals to either I2 plus I3, or we can write it as I2 minus I4 plus I3 plus I4, or it would be equal to I2 plus I3 only. So current in branch AB would be equal to I2, that is 4 by 17. Current in branch BC, that is this branch, would be equal to I2 minus I4. That will give us 4 by 17 minus 2 by 17. So the current in branch I4 is minus 2 by 17, that is I4 is this branch. In branch BT, we have got current minus in the direction. That implies that our assumed direction is opposite to that of the flowing current direction. So that is, if we have assumed that I4 is flowing from B to D, then the actual current would be flowing from D to B. That's why the minus sign is there. So using the same approach, we can find the current in BC, AD and BD and AE as well. The current in AE would be equal to I1. Now I1, as I said before, it is given by I2 plus I3. So we can simply add 4 by 17 and 6 by 17 and we will get as 10 by 17. 4 by 17 plus 6 by 17, that will give us 10 by 17. Now each of these currents will be in ampere. Thank you. The question says that a storage battery of EMF 8 volt and internal resistance of 0.5 ohm is being charged by a 120 volt DC supply using a series resistor of 15.5 ohm. What is the terminal voltage of the battery during charging, and what is the purpose of having a series resistor in the charging circuit? So this is the circuit diagram of this question. There is a battery of 120 volt which is acting as the source battery for charging the battery, that is of 8 volt EMF. Now also there is a 15.5 ohm resistance through the battery, through the source battery in series, and the internal resistance of this 8 volt battery is 0.5 ohm. We have to calculate what is the terminal voltage of the battery during charging, that is, we have to calculate the voltage across this cell. Now we can run a loop and assume that anti-clockwise current is flowing in this circuit. I have assumed I to be in this direction. So let us proceed from this battery. So at point here we have 120 volt potential difference. So I've written 120 volt. Now at this point we can see that since the direction of current that is flowing is from left to right. So this point will be of high potential and this point will be of low potential. So we can write as 15.5 times AI. Now proceeding to this resistor, we will see again that in our assumed direction the current is flowing from right to left. So this will be the higher potential point. So we can write it as 0.5 times I. Now this is the lower potential, that is minus terminal of the battery. So we can write it as 8 volt, minus 8 volt. And now once we have passed this cell, we have reached this same wire over here that we have started. So our loop is completed. Now we can write summation of all this equal to 0. So we will get a value of I as minus 7 ampere. That means our assumed direction of current was opposite. So a current of 7 ampere is flowing in this direction. Now once we have known the value of current in this circuit, so we can easily calculate potential difference across any of these components. Now this is the battery component, this is the charging battery component over which we have to find out the potential difference, terminal voltage of the battery. So voltage across this charging battery can be given by the potential difference across this component. So it would be equal to 8 volt plus, since the current is flowing in this direction, that is the clockwise direction from left to right. So this will be a point of higher potential now. So we can write it as plus 0.5 times the current. So 8 volt plus 7 times 0.5, that will give us a value of 11.5 volt.
The question also asked, what is the purpose of having a series resistor in the charging circuit? The thing is, why do we use a series resistor in the charging circuit? The series resistor limits the current flowing through the circuit. Now without a resistor, the current would be very high due to the large voltage difference between the DC supply and the battery's EMF, potentially damaging the battery of the circuit. By controlling the charging current, the resistor helps in safe and steady charging of the battery, reducing the risk of overheating or overcharging. Thank you. The question says that the number density of free electrons in a copper conductor estimated in example 3.1 is 8.5 into 10 to the power 28 per meter cube. How long does an electron takes to drift from one end of the wire 3 meter long to its other end? The area of cross section of the wire is 2 into 10 to the power minus 6 meters square and it is carrying a current of 3 ampere. Now this question is a continuation of example 3.1, which employed calculation of average drift velocity. Now in this question we have to find out how long will an electron take to drift from one end of the wire to another end, given that there is a current of 3 ampere flowing through the wire, and we have been given the dimension of wire, that is the cross section of wire we have been given. It is of 2 into 10 to the power minus 6 meters square, and the length of the wire is also given, that is 3 meter, and the number density of electron is also given, that is 8.5 into 10 to the power 28 per meter cube. In order to find out how long does an electron take to drift from one end to another, or the time duration that the electron will take to travel 3 meter given a current, we will have to calculate the drift velocity, and time duration can be calculated by dividing the length of the wire divided by the drift velocity. So at first the expression for Vd or the drift velocity can be related to current using this expression, that is Vd equals to I divided by NEA, where N is the number density of the free electrons, I is the current through the conductor, and E is the elementary charge, and A is the cross section area. Now calculating drift time, we can divide it by length, that is L by Vd, and that will give us L times NEA divided by I, that is the current. So substituting the values, we will get a value of 2.72 into 10 to the power 4 seconds, or when divided by 3600 we can get it into hour, and that will be equal to 7.55 hours or 7.5 hours. Thank you.